Okay, throughout the world, there have been global environmental issues, including air pollution, and global warming. Air pollution, global warming, and depletion of fossil fuels. So, to address these issues, many countries in the world are trying to encourage the use of renewable energy, right? And following the global trend, the Korean government announced the hydrogen economy roadmap in 2019. Okay, so in the roadmap, the Korean government is planning to replace 20% of total electricity generation with renewable energy by 2030. So 20% renewable energy, right? So the development of high quality and durable and high performance fuel cell is very important to realize this hydrogen economy. So from the production, this is the production and storage and transport and the hydrogen uses. This is the categorization of the applying the hydrogen into the field. Okay, and in here usually vehicle, the fuel cell can be used in many systems like taxi, bus, or forklift, the drone, something like that. So we will cover in this part. So when we look into the global fuel cell market, the demand for proton exchange membrane fuel cell PMFC is rapidly growing, and the PMFC is good for portable and transportation application. Portable and transportation application, and it will increase rapidly, but it increased rapidly, and maybe in 10 years it will increase rapidly more than now. So this is because the operating temperature of PMFC is very low, under the 100 degrees Celsius, and it is possible to make it lightweight. Then okay, then let me briefly explain how it works. A PMFC consists of membrane electrode assembly in the center. We call this one as MEA. Okay. And gas diffusion layer, GDL, and bipolar plate. This includes the flow field. So there are so many types of this flow field, and we will cover in the mass transport or system design part. Okay, so so we inject this hydrogen gas and oxygen gas. Hydrogen gas is injected into the anode. This is anode, which where the oxidation reaction happens, and in the cathode side, the oxygen gas is injected into here, and at the anode, the hydrogen gas is decomposed to hydrogen, ion, and electrons. And this hydrogen ion is go through this membrane. This is the electrolyte membrane. Okay, electrolyte membrane. and the electron cannot pass through this membrane, so it goes through the external circuit. The electron moves like this one, and in the cathode side, the injected oxygen gas and these three species meet together, and they make a reaction, and the product is the hydrogen and water. The water is the product. So by using this current flow, we use any motor or light bulb in here. Okay, so the goal of this one is making the current, the electron flow from this electrochemical reaction, okay, to use this current. So in the anode, if we see the reaction equation, then the hydrogen gas is decomposed, hydrogen ion and 2 electrons, okay, and the cathode half oxygen gas is met together with the 2 hydrogen ion and electron, and they produce this water molecules. So the overall reaction is expressed like this one. So as you can see, the fuel cell converts the chemical energy directly to the electrical energy. So we can call it environment-friendly renewable energy system. And nowadays, there are many fields where PMFC can be used, and especially for the drone system. The drone system is a very prominent research field, okay, for the delivery or the camera capture, something like that. And the fuel cells are getting much attention for their potential for long time flight, okay, rather than the battery, okay. So many companies in the world, including the Intelligent Energy and Horizon Fuel Cell, Horizon Technology, and in Korea, the Tusan Fuel Cell are trying to develop the fuel cell powered drone system. And also nowadays, Hyundai Motors invent these excellent hydrogen trucks, and they sell these trucks to Europe. And also the PMFC can be used as the forklift power source nowadays, and also the SUV car. And also the fuel cell system can be used in the military microgrid power system and or very small size portable fuel cell system. Okay, as you can see, if we inject this hydrogen and oxygen, and we call this one as fuel. So by injecting this fuel, we generate the electricity, as I mentioned, which is the current, electron flow, and as a product, the water molecules is generated from this electrochemical reaction. So let's see the YouTube movie clip. How does a fuel cell work?
The future will see a huge rise in the range of applications for hydrogen. The energy it provides can now be used on the road via a fuel cell system. Each fuel cell consists of 2 plates separated by a membrane. Oxygen from ambient air is supplied to one side, with hydrogen on the other. The positive particles of the hydrogen atoms are able to pass through this membrane. The negative particles cannot pass through. However, atoms need an equalizing charge. To achieve this, the electrons must change path, and this creates an electrical current. The end products from the chemical reaction are power for the drivetrain and H2O, that is, pure water. This is the only emission produced by this mini power station.
Okay, and there is another movie clip.
Fuel cells are based on it. They use some pretty clever chemistry.
So let's watch one movie clip again from Toyota. This is very high quality movie clip. So the airborne oxygen is used as an oxidant, and hydrogen is used as a gas fuel. Okay, the tank storage pressure is 70 megapascal. So what is the ambient pressure? 1 bar, and which equals to 0.1 megapascal. So the tank can store 700 bar in this tank. It's really high pressurized gas, right? And within this movie clip, they use the refueling time is just approximately 3 minutes. Okay, that is a very good advantage in the fuel cell system rather than the battery system. Okay, very low in the very low loading driving, the battery supply the power. In low loading driving, the car used power from the hydrogen fuel cell stack, and the remaining power is used for the recharging the battery. Okay, from the battery and fuel cell stack, they provide the electricity from these two power sources. This is the downhill. Okay? Downhill, they didn't use any other power. And from the generator, they recharge the battery again. This is stack, and this is one single cell. The airborne oxygen is supplied to the cathode. In here, they attract the cathode, means they attract the electron. So they denote this cathode as a positive electrode, and left side, the negative electrode is the anode. Okay, then let's check what is the fuel cell. The fuel cell. Fuel cell is a factory, right? Factory that produces electricity by supplying fuel. So there are many types of fuel, and as I said, the H2 gas and methanol can be used as a fuel, and methane gas, it can be used as fuel in the depending on the system. So the fuel cell convert chemical energy to electrical energy directly. Okay, and compared to this fuel cell, there is another internal combustion engine, right? Internal combustion engine in Korea, 연소 engine, is used for the power station for the generation of the electricity. And what is the difference from fuel cell? Okay. The chemical plant that converts chemical energy into mechanical energy, and from this mechanical energy they generate the electrical energy. Okay, if this is one of the example, if there is hydrogen gas and oxygen gas meet together directly, they produce they produce the water, right? During this process they generate heat. Okay, so the heat, where does the heat come from? If there is gas reactant and if there is a product, okay, the generated water binding energy is lower than the initial state of hydrogen and oxygen binding energy. So the initial state hydrogen and oxygen binding energy is higher than the product. Okay, so it is smaller than this one. So if the hydrogen molecules have 10 energy 10, and if the oxygen gas have 5, then the product hydrogen water molecule have about 12, right? The amount of 3 is transit to the heat. Okay. So in the internal combustion engine, the thermal energy is transit to mechanical energy, and from the mechanical energy the electrical energy is generated. Okay, so we call it as an inefficient way and complex way. But the fuel cell generates the electricity from the reaction directly. So let's see how a coal power station works, which is one of the examples for the internal combustion engine for the electric energy generation.
The huge building you see behind me is one of Ontario Power Generation's fossil fuel generating stations. This one uses coal. Other fossil fuel generating stations use oil and natural gas to make electricity. In essence, it's a factory that converts the energy from burning coal into a flow of electrons, or what is commonly called electricity, the electricity that powers the province. Coal is shipped to the station by freighter or train, where it's then transferred to the coal yard. There, large machines called tractor scrapers arrange the coal into storage piles. A series of conveyors transports the coal into the plant, where it passes through enormous pulverizers that grind the coal into a fine powder prior to burning. The pulverized.
So the fossil fuel core, right? Core is provided through this one, and this is the grinder, which make a very fine powder shaped.
Coal is fed into a large industrial furnace that is surrounded by boiler tubes filled with water.
Okay, this is the boiler.
The intense heat from the burning coal heats the water in the boiler tubes and turns it into steam. The steam is transferred under pressure at high speed through large pipes to turbines like these. It's this pressure and flow that pushes the blades of the turbine, causing it to spin. The turbine is connected to a generator that contains a rotor. Large electromagnets are attached to the rotor that is located within coils of copper wire called the stator. As the generator rotor spins, a flow of electrons is created in the stator. This produces
this turbine rotation makes electrical generation.
Electricity that can be stepped up in voltage through the station transformers and sent from the station across transmission lines. The steam from the turbine is condensed back to water using cooling water from the lake and pumped back to the boiler where it is reheated to continue the process.
Okay, this is a Rankine cycle, right, to generate electricity. Okay, if you see this one, in the y-axis, the potential energy, and in the x-axis, there is a reaction progress. In the first state, the hydrogen gas and oxygen gas is separate together, and the hydrogen gas is approach to the oxygen gas, and they meet together, and they should overcome this activation energy, and they reach this product energy state. Okay, as I said, the energy of this product is lower than the reactant energy level, right? So how the molecules is composed in the formation of H2 or oxygen O2. Okay, if there is one atom, not a molecule, so if there is a hydrogen atom, for example, and they are far away, and there is no compound bond, it's covalent bond, and they locate high in the energy level in here, and if they approach together and the hydrogen atom access, okay, in the number 2, the stable chemical bond, which is covalent bond, right, and they locate lower energy level, right, and if they meet the distance, it gets narrower, then they have the nuclear. And if these positive charges are meet together and get closer together, and they made the repulsion force, right? So this is unstable. So the two atoms make one composition, one molecular composition in here. Okay, so this is the potential energy of the molecules. Okay, we defined like this one. And let's move on to the basic principles of gas. So there are two electrochemical half reaction. In the anode, the hydrogen oxidation happens. Hydrogen oxidation, and in the cathode, the oxygen reduction reaction happen. And the oxidation reaction generated electron, and they made the electron flow to through the external circuit, and they reach to the cathode side. And as I said, there is a ion transport. This charge, ion transferred through the electrolyte membrane in the center. Okay. If there is anode, cathode, there is a membrane in here, and the electron flow through here, and the ion transport occur in here. Okay, and the first type of the fuel cell is tested in 1839, and the composition of the composition is the two platinum electrodes in a sulfuric acid solution. Okay, in this solution, the fuel cell is demonstrated at the first time, and let's see the unit for each definition. The energy is joule. Okay, we will not use the calorie, and we will use the joule. And what is the energy density? Okay, volumetric energy density is expressed like this one: joule per cubic meter. And what is the power? Power is the speed, right? The energy speed, energy generation speed. Okay, so we use the watt for denoting the power, and watt equals to joule per sec, right? Joule per sec. And the power density is watt per cubic square. This is the volumetric power density, but in a fuel cell we will use the area power density usually. So watt per square meter. Okay, this is the volume, and this is the area. But if you see any paper related to fuel cell, we only use this one. Okay, and the energy is in the battery system. We'll use usually the electricity times hour, watt hour, right? This is energy. And why it is energy? As you can see here, watt is joule per sec, right? Joule per sec. And we times multiply hour. 1 hour is 3600 sec, and it means 1 watt hour is 3600 joule. Okay, we will not use in this course, but it is better to remember this one. Okay, this is the basic principle of the fuel cell. The first time in a sulfuric acid solution, there is a two PT electrode, platinum electrode, and they bubble the hydrogen gas and oxygen gas, and in here oxidation reaction happens, and also electron cannot pass through this solution, right? So they only move through the other external electrical circuit, and the hydrogen ion can move through this solution. So this is the first type of the fuel cell. And we can separate, okay, we can categorize its fuel cell depending on the electrolyte membrane. Okay, so we can separate as five fuel cell in this table. Okay, PMFC, as I said, a polymer electrolyte membrane is used for it, and the charge carrier H+, and the operating temperature is very low, This is the advantage of this fuel cell. And the catalyst is used, the platinum is used as a catalyst, and the cell component means the bipolar plate or the gas diffusion layer or the catalyst support layer, and that the carbon is usually in the PMF6 system. And the fuel is hydrogen, and also methanol. We can use the methanol for this system in the same configuration, and we call it as a methanol, direct methanol fuel cell, DMFC. Okay, if we use this one, DMFC, direct methanol fuel cell. And in the PAFC, they used liquid H3PO4, phosphoric acid, right? Now in here there is a immobilized. Immobilized means if they use a liquid type, right? So they should be fixed in the some matrix fiber. So if there is a fiber like this one, and acid, phosphoric acid should be adhere near this matrix. Okay, but actually there should be loss of this liquid outside, from the inside to the outside, right? Of this leakage. Leakage is very important issue in here. And okay, the other thing is similar, but the temperature is different. And there is a AFC. They use the liquid potassium hydroxide. Also, they are immobilized, as I said before, and the charge carrier is OH minus. Okay, hydroxide ion, hydroxide ions, and also this is very the operating temperature is very wider than the other fuel cell system. And in the molten carbonate, MCFC, they use the carbonate ions, and the operating temperature is relatively higher than the other cell. And okay, this is a high temperature fuel cell and low temperature, okay, relatively, right? And they use the stainless based cell component. Okay, and in the SFC they use the ceramic material, and the charge carrier is oxygen ions and high temperature. Okay, but actually when I check recent paper, they decreased the operating temperature under 500 degrees Celsius. Okay, and there are development for the SFC, PMFC is ongoing. Okay, and the choice of a fuel in the SOFC system is flexible, more flexible than other fuel cell types. Okay, as I said, the electrolyte in the SOFC system is a ceramic membrane. It is very brittle, and the charge carrier is oxygen ion. And like the PMFC, they inject the hydrogen and in the anode, to the anode, and oxygen gas into the cathode, and the electron is decomposed from the anode in the anode side, and the electron goes to the cathode side, and they make the oxygen ion, and they move through the membrane, okay, electrolyte membrane, and the resultant is the same, H2O. Okay, then let's look into the basic operation of fuel cell. The current is proportional to the size of the reaction area, right? Where the reactant electrode and electrolyte meet, right? So as I said, the electrochemical reaction happens in the cathode side, where the reactant, what is the reactant at the side? Oxygen gas. And electrode. Electrode means the pathway for the electron current, right? Electron flow. So for the electron, and the electrolyte is used for the pathway for the H plus proton. Okay, they should meet in one side, so they reach to make the water, okay, from this one. So these three components should meet in the one point, and only at the site the reaction happens. We call this one as a TPB, triple phase boundary. Okay, this is the TPB. Okay, to know about the TPB, we usually use the cyclic voltammetry. Okay, we will cover it in the next in the characterization part. And converting fuel and energy source into flow of electrons produces electricity. Okay. Electrode, high specific surface area. So in the electrode, usually in the PMFC, it is very important to widen the reaction site, right? Reaction site. So in the electrode, usually the porous layer is used, and for the gas contact, which means that the O2, for the O2 penetration into the electrode, we should use the, not should, but actually for the high efficiency we use the carbon material, and on the carbon material there is a PT, platinum, for the catalyst. Okay, there is a PT, something like that. This is a PT, and the upper one is the carbon. Okay, they should connect together. Carbon. Usually we use the Birkin carbon, but nowadays the glassy carbon is used for the durable electrode. So by using this electrode composition, the gas can penetrate into here, and we can maximize the surface area of this PT particle. Okay? And the size of this spherical carbon is the 50 nanometer, and this yellow one is about 5 nanometer. Okay, and the fuel supply, oxidation electrode. Okay, let's skip it. And there are 4 steps for the reaction. Okay, let's see. The first step is fuel in. Fuel in, reactant transport. The reactant should be transported through the porous material, porous electrode, right? And the second is electrochemical reaction. The reaction happens. And the third one is transport, right? Transport. Third, H plus electron, the transport. The two species should transport to electrolyte or the electrical circuit. So there are 2 components, ion and electron. And finally, the product should be removed. okay, the products should be removed. Okay, that is the steps for the electrochemical reaction and input and output. And okay, we can separate the overall process into 4 steps. Okay, when it comes to fuel cell performance, we can measure the performance by using the power. Right? Power is VI, right? Voltage time current. And this working voltage, okay, we usually use the operating voltage. This is operating voltage. And this is the ideal voltage. We denote it as E. Okay, this is ideal voltage. This is ideal voltage, which is also called the reversible voltage. Okay, the reversible means ideal. Okay, and there are 3 types of main loss, right? First one is activation loss. So activation loss is that the loss due to the electrochemical reaction. First one, activation loss, electrochemical reaction. Okay, if there is a reaction energy level like this one, okay, we should go over through it, right? This is activation energy. So from this side, from the defect, the activation loss happens. Okay, the second one is ohmic loss. Okay, as I said, there is 3, right? Ionic and electronic conduction. Okay, from the ion and electron conduction, we should have some other resistance. Okay, that is the ohmic loss. And lastly, there is a concentration loss. Concentration loss is due to the mass transfer. If there is a porous electrode like this, and there is a reactant, right? Reactant should approach near this catalyst, right? And if the reactant react fast, and they should be removed. This is the product. They should be removed, and the reactant go fast to near the surface, right? But there we can describe as a concentration loss, as a resistance, right? And the other thing is also resistance too. Okay, so we will talk about this series. This in series. First one is reversible potential, and what is the activation potential, and what is ohmic loss, and what is the concentration loss. Okay. So chapter by chapter is composed in this term. Okay, so the fuel cell is designed to operate at or below the peak power density to improve the voltage efficiency and reduce power density. No, not for. Okay, in reducing power density. It leads to the reducing power density. Okay. What I mean, what this sentence means is that in this graph, okay, the fuel cell voltage is plotted in the first column of the y-axis, and in the x-axis the current density is located, and the fuel cell power density is in the right side. In y-axis is the power density, and how the power is expressed. Power is VI, right? So actually we should use a J, but actually in this step just use I. So if there is one specific point, if there is one specific point, means not here, okay, if in the IV curve, this is IV curve, if there is a voltage, then there is a corresponding the current value, right? If we okay, then if we multiply these two values, that though we can get the power density curve, right? This one in here, the power, peak power in here, right? Then this voltage is the peak, makes the peak power. But as the sentence said, and usually we did not use the 0.4 or the 0.2, something like that, because for the increase the voltage efficiency, right? Okay, so usually in the commercial field, I heard that usually the 0.6 or 0.7 is usually used in this reason. Usually the fuel cell is operated the commercial field. Okay, so we'll cover the ideal thermodynamic fuel cell in the chapter 2. Usually in ideal the current does not shouldn't decrease depending the voltage shouldn't decrease depending on the current density. That is either case, but actually there is many types of loss, right? The first one is activation loss. Okay, so the voltage is dropped like this one, and in the ohmic region there is a ohmic loss. So, and finally there is a concentration loss. This is a rapid drop. So as the current density increase, always the fuel cell voltage is decreased. So remember that. And actually the goal of the fuel cell research is to reduce this amount of the loss at each part. In the activation region, it depends on the catalytic activity or of the catalyst, right? So the catalyst, the high performance or high activity catalyst can reduce this loss. So the cell voltage will increase like this one. Okay, and if we develop very thin and there is a very low loss resistance in the movement of ion and electrons, then the ohmic loss is expressed like this one. Okay, and if we can make a very mass transport than the conventional one, then the performance is expressed like this one. Okay, so by development many materials, our goal is increase the performance by reducing its loss. Okay, that is the goal of the fuel cell research. So the first part is about the thermodynamics. The thermodynamics, the conversion of energy from one form to another, a field in energetics. And the fuel cell is an energy converter. So what is the fuel cell thermodynamics? The fuel cell dynamics is the key to understanding the conversion of chemical energy into electrical energy. Okay. So from this one, fuel cell thermodynamics, we can determine whether the fuel cell reaction is spontaneous. Reaction happens or not. And automatically, spontaneous means automatic. So the second one is a present maximum voltage limit value. Maximum voltage limit value means, as we see in this graph, there is a maximum value that is the ideal value. Well, we cannot anticipate the maximum voltage. And the present, the theoretical ideal case possible in fuel cell. Okay, just ideal case. This is the only ideal case. And the understanding fuel cell performance requires knowledge of the dynamics and dynamics like a fluid dynamics. Okay, then thermodynamic. Let's start from the thermodynamic review. So what is the thermodynamics? Richard Feynman said, we don't know what energy is. Okay, he don't know, then we don't know too, right? So we only compare the comparative method in the comparative method, and based on the law of thermodynamics, and use enthalpy. But we don't know exactly what enthalpy is, but we can compare the enthalpy value or free energy value, something like that. And the energy, temperature, pressure, volume, how are they related together? We will, based on this knowledge, we can anticipate some heat generation or power generation, something like that. And firstly, we start from the internal energy. Internal energy is denoted as U. Atom and molecular scale, microscopic motion, and interparticles. So interaction related energy. Okay, internal energy is interaction related energy. So the chemical bonds, it includes the chemical bonds and the relationship between the molecules. Okay. So internal energy conversion amount, okay, we can anticipate this one from the thermodynamic first and second law. If we see the hydrogen tank, right, in our view, there is no apparent macroscopic energy change, right? But actually, it has significant internal energy. It contains really significantly high energy, right? So the internal energy is associated with microscopic movement, or we call this one kinetic energy. They move, right? They move, the molecules. We call it kinetic energy. And interactions between the particles, right? Interactions. The chemical and potential energy on the atomic scale. So let's check the first law of the thermodynamics first. You already know about this one. Okay, energy conservation, right? The energy of the universe is zero. The change of the energy. So if we make a system, then the other area is surrounding. Okay, system surrounding. So D system plus D energy surrounding should be 0, right? That is about the first law of the thermodynamics. And we transform like this one, and we call this one D energy system as du. Okay, this is an internal energy. Okay, if there is a dq, some quantity of heat is supplied to a specific system. Okay, then the system store the energy inside, and the remaining one is go outside as a work. Okay, so dq equals to du plus dw. Then this is the same with this one. Okay, because it is harder, it is easier to think about it, minus D energy surroundings. Okay, so from just remember this one, this scheme. So du equals to dq minus dw, right? And the work, we usually think about the mechanical work. If there is a cylinder and if their internal pressure is P, and if the cylinder is moved dx, okay, in the length, and we how can we define the work? Work is F dx, right? Fx distance, and F is PA. The area of the cylinder is A, PA dx. A dx equals to PdV, right? A dx equals to PdV. So PdV is the D work. Okay, so PdV. So we can convert the internal energy to this one. Okay, this is the internal energy. Okay, just to remember this one rather than this one. Okay, and what is the work and heat? Work and heat. The energy is the energy in transport, energy transferred between the surrounding environment. Okay, this is this transit, right? That means this transit. And work, when a force is applied to move a certain distance, this energy is transmitted. That is F. Work is force F to move a certain distance. We use the dx in front of the example. And heat is energy transfer by temperature difference. If there is a very cold room and if there is a very hot room, then the energy is transferred from the hot room to the cold room. Then that the amount of heat energy is heat, right? We call it as a heat. And the second law of thermodynamics, the heat cannot be converted to 100% work. Okay, can draw we can draw the second law like this one. TH, which is the high temperature. If there is a TH, high temperature, and there is heat engine, then they generate work by supplying the QH from the hot space. And the second law means that this is not possible. This is impossible, right? Only this case is possible. There is a low temperature region and the QL is exposed to the low temperature region. Only this case is possible, right? So if we insert QH, then there is a loss, right? So there cannot be any 100% mechanical or chemical conversion. And okay, okay, let's remove this one. And the second second law of thermodynamics. Okay. The entropy. There is a very important concept in the second law is entropy, right? The entropy is defined as the number of possible microstates in the system and the number of possible ways to configure the system. This is the definition of the entropy, but we don't need to remember it, okay? And the entropy measures the disorder, okay, the amount of the disorder, and the simple, okay, there is a very microscopic aspect, and but we will not use the microscopic aspect. We will use the macroscopic aspect. Okay, this is a microscopic. But we will not use it. Just to check it. Okay, S is the total entropy of the system. S is entropy. Okay, S entropy, and K is the constant, Boltzmann's constant, and omega denotes the number of possible microstates accessible to the system. Number of the possible microstates. Okay, for example, if there is the entropy of this 100 atom perfect crystal, this is a perfect crystal, is 0. Why? There is only one possible way to arrange the atom like this one. Okay, so if we insert 1 into this omega, then S should be 0, right? The entropy is 0. And how about this one? In the right hand case, when 3 atoms are removed from the crystal and placed on the surface, the entropy increases, right? Because there is the number of possible ways is increased. So so how can we calculate this one, the entropy of this system? It is complicated, but it is possible to calculate the number of possible ways to take 3 atoms out of 100 atoms. Okay, what is this one? This is the combination. So from the 100 we can select 3. So how can we calculate this one? Like this one. Okay, the taking n atoms out of jet atoms, right? Then 100 minus 3 factorial and 3 factorial and 100 factorial, and the number of the result of this omega is this one. Is this, and if you calculate it, then the entropy can be calculated as this one. Okay, this is the way to calculate the entropy, but we will not use this one because it is more complex than we thought. So we only use this way, ds. Only we in comparison way, we only care about the difference between these 2 states. If there is one state and the second state, we only consider the difference between these 2 states. How can we measure it? Okay. this one. So the change of the entropy in the constant temperature is defined as like this one. Okay. So in a constant pressure reversible heat transfer system, the entropy change of the system. So what is this? dq reversible ideal case, only this case is ideal, TdS, but we will use it. Remember that dq equals to TdS. In the second law of thermodynamics, the change in entropy of the system and its surrounding system increases or becomes at least zero. The zero is the ideal case, zero ideal, and in real process always it increase. Okay, but just remember that the ideal case in here, okay, this one. Okay, then and as I said, there is a dq, the definition of the internal energy, du equals dq minus pdv, right? And we now use this one, dq equals tds. And then the u is the function of entropy and volume, right? And if we differentiate, divide this one, this ds, okay, while we consider the volume as a constant, if we divide the ds in the left and right together, and we get the t. Okay, and if we use if we assume that the entropy is constant, then ts goes to 0. Okay, if we use as constant, then it goes to 0, and du ds is here. Here it is not. Okay, dv. If we divide the dv on the left and right together, and minus p is remained. Okay. So the difficult, it retains the difficulty measuring the entropy and volume, right? So we convert it by measuring in T and P. Okay. Okay, this is a T and this is a P, right? We use the T and P for the energy change, right? That is the original definition of the Gibbs free energy. And the Gibbs free energy then is defined as like this one. But just remember this one, G equals U minus TF plus PV. Okay, this is the Gibbs free energy, and the Gibbs free energy, if we make a perfect differential to this G, then du minus TDS minus STD and plus this one, right? And du equals to TDS minus PDV, right? Then we can write like this one, TDS, okay, TDS and minus PDV. Then now we only have the minus STT plus VDP. Okay, so which means that the result okay, this result indicate that to know about the Gibbs free energy change, right? Change of the Gibbs free energy, we only consider the change of pressure and temperature. Okay, by using this one, the difference because it is easy to measure the pressure and temperature. By using this change of these two property, we can define the Gibbs free energy. Okay, then what is the enthalpy? Enthalpy is originally defined as this one. Okay, in Gibbs free energy, there is no S term. As we learned in the thermodynamics in the undergraduate school student, then H is defined as U plus PV, right? But actually the original definition is this one. So this is a P, right? So remember that H equals to U plus PV. And if we make a differential, perfect differential, then du plus PdV plus VdP. Then the du equals to TdS minus PdV. If we insert this one, then TdS and minus PdV and PdV is cancelled out. So dH equals to TdS plus PdP. Okay, this is the result of this calculation. Okay. And also there is a Helmholtz free energy, but in this course there is the Helmholtz free energy is not considered in any other field in here, so just to skip it. And then what is the meaning of each concept? Okay, energy. Okay, in this chart, the meaning of that is expressed in word chart. Okay, what is the internal energy physical meaning? As the energy needed to create a system. Okay, energy create a system. And we don't care about this one, but just to see, Helmholtz free energy needed to create a system, right? And additionally, energy provided by the environment, Ts, right? So minus Ts means the energy provided by the environment. Okay. And how about the enthalpy? Enthalpy, okay, you should remember the enthalpy and Gibbs free energy. Gibbs free enthalpy H equals to U plus PV. And firstly, energy needed to create a system, and plus the work needed to make a loom, right? PV to make a loom for it. And the Gibbs free energy, the total energy, create the system. Same one, create the system. Energy create a system and make a loom for it, enthalpy, make a loom. And finally, the energy provided by the environment. So minus Ts means this blue one, and orange one plus PV is the work needed to make a loom for it. So U plus PV minus Ts is Gibbs free energy, and the meaning of that Gibbs free energy. And we will check how the Gibbs free energy in the fuel cell reaction. Okay, before checking that, let's see what is the more which properties exist, how can we categorize it. Firstly, intrinsic property like temperature and pressure. Okay, and this property is independent on the size of the system. Okay, not related to the more or the number or the mass. And what is the intrinsic property? In extrinsic property, that is the depending on the size, system size, and which is internal energy and entropy. And we use the U, okay, capital U, and entropy S, right? But how can we make this extrinsic property to the intrinsic property? Okay, then that is the concept of molar quantity. Okay, molar quantity means per mole, how much the material has in the aspect of the internal energy or entropy or enthalpy, something like that. So we use this one, G and S and V, volume, right? If we divided the number of moles, then moles then we can get this one. This is the molar quantity. Okay, so per unit moles, we can express its concept or its quantity like this one. And delta means the changes between initial and final states in the thermodynamic process. And if we have, for example, if we have this one, we know about it. If there is a water generation formula, okay, a reaction happens, then the Gibbs free energy per mole is minus 237 kilojoule per mole. 1 mole of the hydrogen gas. Then what is the energy change? Okay, let's see this one. If we have 1 molecules of 1 moles of the hydrogen gas, and the oxygen gas is react to generate H2O. Then if we have 2 hydrogen gas, then 1 oxygen gas participate in this reaction, right? And how about that? If we have the 5 moles of the oxygen and it react, and what is the energy exchange, energy change in this situation? Then we have 5 moles of oxygen gas and then 10 moles of the hydrogen gas. So if we multiply this 10 to the molar quantity, then we can get this one. And something like that. We can use the intrinsic property from the extrinsic property. Okay, then let's check what is the standard state. Standard state, STP. We usually use STP. Standard temperature and pressure, STP, right? So the room temperature is assumed to have 25 degrees Celsius, right? Okay, 25, and okay, this is the Kelvin, right? And atmospheric pressure is 1 bar. I just said it's better to remember that 100 kilopascal, which is 0.1 megapascal. Okay, 1 bar means this one. Okay, and 1 bar and 1 atm is not exactly same, but actually we just think about that is a comparable and similar one.